So today we'll finish recursion and maybe start generating functions. On Tuesday we'll do some more on generating functions. Do partitions maybe if you have time. But this will be all in the final, like generating functions and partitions are important topics. And I will mostly follow Grimaldi on these things. So you can read the book. My homework set today also will be from the book. Okay, so let's do the one case that we left last time. So this is second order recursion. It's actually recurrence, I guess. Recurrence equations. Last time I told you how to solve a typical second order recurrence equation. I also showed you how these equations shows up. So one of the cases was Fibonacci sequence. So this is slightly different, but it's good to solve this one so that you can pretty much solve anything similar to this. So solve the recurrence relation. Last time I think I set up F01, but this will be slightly different. This is shifted by 1. This is a choice you make with indexing. So this is the Fibonacci relation, but we are going to assume F0 is 0 and F1 is 1. Just to go with the book's choices. Last time we had F0, 1, F1, 1, but that's just a shift of this, okay? While we are solving this, this is Fibonacci. Again, it's a choice by 2 ends, I guess. It's a choice with the initial value. But aside from that choice of initial value, this is a standard Fibonacci sequence. And this is the sequence that showed up in when we look at the rabbit population with the rule that a baby rabbit grows after a month to mother and then gives birth after become immature. So this was the equations. So if you look at the lines, you get Fibonacci sequence. So what this is saying is that start from here instead of original one. Okay, so you can do that. It's just a choice where you start. And the rule is that if you sum these two, you should get the next one. Okay? Now, last time we've seen that anytime you have a sequence with some initial values, the solution is, you assume that the solution has a just generic form, looks like this, some A, R, N, for some A and I. This was the generic solution for first order recurrence. Of course, this both R and A should be non-zero so that this is non-trivial. If it is 0, it will be 0 everywhere, which we know it's not. Right? So this is the generic solution for a first order recurrence. By putting this in, what you get is something like this. Now this is an equation involving R and R, A and R, and then you factorize this part. You get an equation like this. By our choice that A and R is non-zero, this part is non-zero. So this forces this part to be 0. Now this is called the characteristic equation of the equation. This equation is a second order polynomial quadratic equation. Because of this is being second order, that's why we call these recurrences also second order. Okay? So with a recurrence characteristic equation like this, you find its roots. Let me remind you that this has roots 1, 2. Like this. And this discriminant part, this thing, there are 3 cases for this. So delta positive 2 real roots, delta 0 repeated root, and delta negative complex roots. So these are the 3 cases we'll be studying. And for this particular question, you can look at the roots. Is v square like this. So you get 1 plus minus square root of 5 over 2. Now, although it looks like square roots are involved, it's still they're both real numbers. So you actually have 2 roots. Let's denote them with alpha and beta. These 2 numbers are both real numbers. So you have 2 distinct real numbers. So this is the case we're at. This is usually called case A. Now we have B and C. In case A, you say the general solution is Fn is equal to some constant times first root to the power n, some constant times second root. So this, I use alpha beta, but it's actually, you can write it this way too, if you first. Okay, so this is your solution for general solution. Of course, this involves A1 and A2, so you have to solve them and to finish the proof, to finish the solution. To solve them, we need the initial values. So these are the initial values we have. So to solve A1 and A2, we use F0 and F1, which are given specifically with these values. So what you do, you set up F0, F1 equations. So F0 equation gives you this. When you put 0, you get this A2. And then if you put the A1, you get this. 1 plus square root of 5 over 2, A2, 1 plus square root of 5 over 2. So these are the equations you have. You can do a couple of different tricks. You can multiply this equation with this and cancel out. You can take subtraction. So you get minus 1 equals to 0. 1 plus square root of 5 over 2 minus 1 minus square root of 5 over 2. A2. And the difference here is square root of 5. So A2 becomes minus 1 over square root of 5. And then A1 is the minus of A2 from the first equation. So it's square root of 5. So the answer to solution, specific solution, let's call it, for Fn is just this. 1 over square root of 5, 1 plus square root of 5 over 2 to the power n minus 1 over square root of 5, 5 over 2. And this is true for all n bigger or equal to 0. Okay. For n equals 0, you can quickly check that you get 0. For n equals 1, it's a little harder, but you will get 1. So it is not only satisfy the recurrence, but also it satisfies this initial values. That's the point. So now we can solve the Fibonacci. That means we can actually solve some word problems that involves this. One of the word problems that is given in the book is this dominoes problem. I like this one. So suppose we have a 2x2 chessboard for n is positive integer. So we wish to cover this board with 2x1 dominoes, which can be used in a horizontal way or a vertical way. In how many different ways we can cover this? Such a board can be covered. So this is 2 by n, so the answer will be in terms of n. One can make it more specific by, sorry, this is 2 by n. By specifying some n, say 100 or 99 or something. So you will have to give an explicit formula. So 2 by n means you have a thing like this, and then you can cover it with dominoes using them vertically or horizontally. So there are many different ways of putting them. As you see, you can put vertical, doubles, and blah, blah. So there are many choices and how to cover it. So this part is n units. So this will be 2 units, 1 unit, and so on. So n units. How many different ways you can cover it? This is the question. For these kind of problems, these are called word problems that involve recursion. You can make a lot of nice word problems that involve recursion using graph theory too. So this is a very rich area for problems. You can make many, many interesting questions involving the recursion. The best way to attack this kind of word problems is first try to see with some small values of n what these numbers are. And if you're lucky, sometimes these numbers look like something. Like if you find the numbers to be 1, 4, 9, 16, and you start thinking that, oh, there must be something which makes them squares, right? if you find the numbers being this, then you're like, oh, that must be Fibonacci. And then you go to the second step of trying to prove it. But first, make some cases. So for n equals 1, this is the only way. For n equals 2, you have two choices. For n equals 3, you have this. You can do this. So you have three choices. For n equals 4, you have how many we did? Or Taylor unit. So we have 5 choices. So which sequence it looks like? So the number of choices, let's say, let an denote the number of ways to cover a 2 by n board, as in the question. So with these dominoes, so we see that A1 is 1, A2 is 2, A3 is 3, A4 is 5. So which sequence it looks like? Any answers? Fibonacci, yeah. So it looks like this sequence, slightly shifted, so it starts from here. But aside from that, it's the Fibonacci sequence. So that means we should be able to, I mean, if we're lucky, there will be Fibonacci sequence. But to say that I found 5 values and it looked like this sequence, so it must be that, is not acceptable, right? You have to show why it is actually Fibonacci. So to show why it's Fibonacci, you need to show that an actually satisfies that recursion. So what was the recursion for Fibonacci? That an is sum of the previous two terms. So there must be some argument that you can use to conclude that an will be an minus 1 plus an minus 2. Anybody sees how that argument can be done? So how I set up? So if this is an, like up to n, if I want to add, I can do this way, or how I should look. Or it could be this way. How about the? Huh? There's a slight problem of trying to think with adding. I will prefer if you set your argument with some fixed n and try to write it in terms of smaller ones. So can you change your argument so that all the ones which covers n by 2 is some covering previous this or this way, or can you think the same argument by taking out, not adding? Hı hı.
Eğer en sondaki x'e
Uh-huh.
olarak çıkarttığımız zaman n artı 1 kök n eksi 1 kök.
Let me write that. Keep your argument. Okay, so we learned counting. In counting, as one of the important things was to separate it into cases, right? So an is the number of ways to cover a 2 by n board. Now these coverings are all different, right? But you can say there are exactly two possible cases that this covering can be done. First case, you can say these are the ones where
using n minus 1 dominoes
mm-hmm.
using n minus 2 dominoes.
Yes, but can I specify which will give me n minus 1?
The last domino is
Mm-hmm. Where the last one, the last domino is vertical. So if the last one is vertical, you specify that this one is vertical. Okay. The other one, it can be either vertical or where the last domino is horizontal. The last domino. So it's like coming like two dominoes, but it's horizontal. Dominoes are horizontal. So it's either this way or this way. The last part is either that way or this way. There is no other possibilities. And these two possibilities don't intersect. They're distinct possibilities. So the counting problem is separated into two possible ways. This one or this way. Now this one, as you said, you take one out and the rest of it I am free to do any way I want. But that's a n by n minus 1 times 2 domino. So that means I can say this is equal to n minus 1. And here I have what is left is n minus 2. So this will be, the number here will be an minus 2. So you can actually easily see that an is equal to an minus 1 plus an minus 2. So it satisfies Fibonacci. So it satisfies Fibonacci formula. Now, if you have a Fibonacci recurrence, also we have A0. We already decided that A1 is 1, A2 is 2. So it's a little bit shifted. So I can conclude that an is just the shift of the Fibonacci. So n plus 1, just the shift. So that's what you'd say. Sorry. So normally this appeared like in the third stage of F3. I had that, and now I erased it. But this was normally F3. So now this happens in A2. So that means there's a shift. But because we already solved Fn, we can conclude that this is going to be just this. You just write the formula we just try. So this becomes the answer. If you know the Fibonacci, you write it. If you don't know it, you find the solution. You write the solution. Okay, there's a very nice argument here which relates Fibonacci sequences to this theorem, Lame's theorem. This was one of the things we discussed during the semester about the Euclidean algorithm. what is how many steps you need for the Euclidean algorithm to complete, to give you greatest common divisor. So Euclidean algorithm was this algorithm that gave you greatest common divisor. You can estimate it using Fibonacci sequences. I can do it, but I think it will be a little bit distraction. So you can read it from the book. This is very nice. It's called Lame's theorem, and it explains how Euclidean algorithm can be the steps. How many steps you need for Euclidean algorithm can be estimated using Fibonacci sequences. So I'm not going to do it. Instead, let's do some more recursion. So what I want to do is, so case B, maybe case C in the book. I think this is case C in the book. Repeated roots. Okay. So this is easier than complex in some ways. So I want to do first this case. And now we'll do case B, which is the complex case. The best way to do this actually is to do one example, and then we'll try to explain why it works. So solve the recurrence relation an plus 2 4an plus 1 minus 4an, where n is bigger or equal to 0, and h0 is 1, a1 is 3. So this is a recurrence, again, second order recurrence. It looks exactly like the ones we solved before. There is no difference in the setup. But when we face the characteristic equation, we'll see that there will be only one root, and we'll see how to handle that. Okay, so the solution is, again, you start with this. And once you put this into your an equation, you will get here a Rn plus 2 for a Rn plus 1 minus a Rn. And as we did before, you factorize Rn. And now you get r squared minus 4r plus 4 equals 0. Let's wait. So this part is non-zero. We get this equation. And the roots here, either you can see it with the root equation, that this part becomes 0, that's why you have only one root. Or you can factorize it as this. So you will see that this is like unique root, only one root. Okay. So you don't get repeated roots, you have just one root. So what goes wrong with one root? You cannot write the general equation with two unknowns.